So I will be talking about causality and streaming data, and this is really a joint work with a lot of people. So Rune Christiansen, Niklas Pfister, Nikolai Mainshausen, Leon Bottou, Dominik Rodenhäusler, and Peter Bühlmann. So what I will be trying to do is the following. So imagine that you have your stream of data, and we are now in the chance of modeling this data, and we observe that this is not IID. We have seen a lot about change point detection in the anomalies in the last talk. So what I want to make here in this talk, what the statement I would like to make is that this can actually be quite a bit of an advantage. So the overall theme will be, let us try to exploit this non-IID-ness of the data. And how are we going to do this? So if we have our data stream, there are two ways of handling this heterogeneity. And the first one is to really control the changes in the stream yourself. So what do I mean by this? You more or less conduct an experiment. So funnily enough, this is, by the way, the Photoshop picture. This is the real one. So here, this is what are we thinking of. We are thinking about a data stream where you can really have control about the data that you're collecting. And the second theme that I would like to talk about, this is the second part of the talk, is if you cannot do this, so you receive the data stream, but you cannot actively intervene on it, but you see some natural changes. I read up a bit on this story, the Yangtze River, and I thought it might be appropriate to use quotation marks here for natural, because it turned out these were not so natural. But this is something that you cannot have control about. Okay, so let's be a bit more concrete. What do I mean by this? So the first part, control the challenges in the stream yourself. What I would like to do now is to explain this with an example. So this is blackjack. This is a small collection of the rules. If you don't know the game, this actually doesn't hurt, because the goal we are trying to solve now is to say, well, we are going into a casino, we have no idea how this game works, and our stream of data will be games that we are playing. And after each game, you will receive some sort of feedback that is just the money, whether you have won or lost the game. And you don't know anything about the rules. Okay? So this is another description of this data. So there is something like a deck that is in a certain order that, of course, you don't know. There are some hidden cards, right? So you're playing against the casino, you're playing against the dealer. This is also something you don't know. There are some open cards. This is what you do know. Then you make some decision, and at the end, you either win or lose money. And this is a lot of, this is basically here including the rules that you also don't know. So a lot of these things are actually just there. This is the data generating process that you don't have any idea about. But this is your controlled experiment. So the only thing that you can change is you can make a decision based on the open cards. What is a decision in blackjack? So you can say, I take another card, I double down. You have a couple of options depending on the scenario. So this is basically the green color that you put into the river. So this is what we can control. Now, a tiny bit more like mathematical. So what is the data stream? We should really think of the games here. We have an underlying data generating process that we don't know, and this is the thing we can control. This is known. So this is the probability of a decision given a game state. And then we have some objective. This is the money that we are making, and this we would like to be as large as possible. Okay, so what do we observe? We just observe our stream of data here. So these are the open cards. These are our decisions. It's either hit or stand. There are a lot of things that we don't observe, and then we just receive as our feedback, we receive, well, have we lost the game or have we won the game? What is the objective? Well, what we want to do is we want to now say, well, we have a current strategy, and what we would like to do, right, is we want to win as much money as possible. And you can now think about that. You start with a certain strategy, and you would like to update it. So you would like to say, well, maybe you lose a lot of money, but after having played a lot of games, you learn something about the underlying data generating process, and this you would like to exploit. So what we want to do formally is we want to replace our strategy, p of y given x, by something else, and then we would like to know, well, what is the expected loss under this new strategy? Okay, this is all assuming that this is the thing that we can control. Now here comes sort of the key idea. I know that this is a trivial thing. It sounds like a trivial thing, but I will later very briefly talk about an application that we looked at in an advertisement. And this was really the hard part. So the scientists really had to go into the company and had to sort of convince the engineers to randomize. Why is this important? So imagine that we have our strategy, and imagine we think we know the system pretty well, and we have our deterministic strategy that we're always playing. Then you can never answer these questions. You can never answer, well, what would happen if we would play a different strategy? How much money would we make then? You can only do this if you randomize. And this, I mean, here in this setting, it of course seems a very natural thing, right? So what you do is in the casino, you don't know, so you play a bit of a random strategy, and then you learn something about the system. However, in real-world systems, this is the experience we made, is that of course people think they already have the best strategy, but maybe they don't. And here it's really the hard part, is to convince them, well, randomize your strategy, and then afterwards you can actually analyze whether you already have a good strategy or not. How do you do this? This is not trivial math. This is the only formula that I'm going to write down, but I just wanted to show you how simple this is. What we want to do is the following. We want to compute the expected value of the loss function under the new strategy. Okay? So what we are doing is as follows. We just write out this integral. This is our new strategy, and now the point is we don't have data from our new strategy, right? We only have data from our old strategy. And now what you do is you just multiply and divide by the old strategy p, and now here comes the key point. If you look at this ratio, this is the sort of the data that you receive under the new strategy, and this is the data that you receive under the old strategy. This is basically the same thing. There's only one component that changed, and this is your strategy p star of y given x. The rest is of course the same. The data generating process, sort of many parts of this remain the same. So the rules of blackjack will remain the same. The way the deck is shuffled will remain the same. All of this is the same except for your strategy that changes. And then if you look at this, then this is suddenly something you can approximate, right? Because now we have an expectation with respect to our old strategy. So what we can do is we can just approximate this and saying, well, we take the experience that we have, and we just reweight these data points. This is nothing new. It's not that we came up with this. This is of course studied a lot, but this is showing you, well, if you sort of intervene on the stream, you can actually gain something. Okay, so now I skip all the details. Many of you know these things anyhow. So of course you can also construct confidence intervals. So this is something that you can do, so that you know, if I sort of try out a new strategy, I have an idea of about how much money I make, and even know sort of in which areas this effective value will probably lie. Good. Then in practice, what we want to do is we want not only to answer these questions, well, what would happen under a new strategy, but we want to find the best strategy, of course. And this is also something that you can do very easily. So here we are trying to find the best P star. So what do? We can, for example, do some gradient ascent. So what we do is we parameterize our strategy, compute gradients, and then just optimize. So we want to find the theta such that the expected loss is as small as possible, or we're making the most money as possible. What you do, you just compute the gradient and optimize step by step, and then there's of course the whole machinery that kicks in. We have to choose step sizes and so on, and we have to think about how to make use of confidence intervals. This is also something that is known. Now here comes the second idea. If you want to do this efficiently, what is the best thing you can do? Well, if you go to the casino, you can play 1,000 games, and then maybe you think, I understand something about the system, and then you update your strategy and again play 1,000 games. So what will be the case here is that actually the point is that you constantly keep changing the stream. So if you play a couple of games, you already learned something, and you can maybe adapt your strategy a tiny bit, right? So what you will find is that you have this online setting where you receive data, then you do one optimization step, maybe you receive new data from the new strategy, and then all these like historic data you're using again for updates. At the end of the day, so mathematically this improves the estimation, of course, because the new data points are in the region of interest. So of course it's easier to estimate a tiny change of strategy compared to a large change. Then it's also clear this is we pay a less cost, right? We are continuously improving the system. At the beginning in the casino we will lose a lot of money. Then we are updating our strategy, we will lose less money. So if you just look at the summation over all the money that we lose, of course, such a strategy of always updating our system, of course, loses us less money. Good. How does this look like? So this is learning blackjack. This is really, I mean, if you like, it's a small exercise that you can implement. So what do you see here? First of all, this is 0. This line here is 0. And what we see is now we play a lot of games. So on the x-axis are the games, and these are like always 1,000 games. So this is the strategy after 1,000 games, I think 11,000, 21,000 and so on. Now what you see here is, this is a very nice mathematical result, I think. What you see is the performance of the optimal strategy. So blackjack is solved in the sense that you know, if you have perfectly shuffled cards, you know the perfect play depending on each situation. This is just a mathematical paper, if you like. And what you see at the red line is the outcome of this optimal strategy. What is good news for the casino is that it's on average below the line, right? On average you will lose money. But if you ever want to go to a casino, I suggest to play blackjack, because this is the game where you apparently lose the least amount of money. So this is what you can see, and this is what we can compare against, right? And now what you see in the blue line, this is our current strategy that is always updated. So this is our stream of data. So here we are like looking at a certain strategy, and then we are updating, and at some point we improve, and we are actually getting close to the optimal strategy. And again, without knowing any rules about blackjack, right? You just go into the casino and try something out. And then I think this is sort of not spectacular, but I think it's pretty nice. You can also compute these bounds, right? You actually know what will happen. So you play until a certain number of games, let's say until here, and then you are planning to update your strategy. And it's very simple math to just compute these confidence bounds for your updated strategy. So this is how you should read the figure. So you always plot these bounds before you actually start changing your strategy, and then what you will see is that in most of the time we actually lie within these bounds. So again, I should say that these ideas, I mean, they exist in various forms. I will try to argue why this causal point of view has an advantage, but of course you recognize like inverse probability weighting, reinforcement learning, Horvitz-Thompson estimators, and so on. And I'm a bit sloppy. I apologize for this. With references in these talks. In this talk, we are a bit more careful in this paper and also later. We were really motivated by a problem that I'm not sure whether I would be still motivated to work on this today, but this was at least a couple of years ago. This is what we looked at, and this is the problem of advertisement. So how does it work? This is an advertisement in, let's say, in a search engine. So you have something like the user intention, which is hopefully hidden to the big companies like Google or Microsoft. And then you have a lot of user data. And this is not hidden, and this is actually surprisingly much. So they don't know only, of course, time of day, time of year. This all plays a role. They also know quite a bit about the user. It's a tiny bit scary, I think. But then one part that is obvious, of course, is they know the search query. So user goes to a search engine, searches for organic oranges, and then, of course, this is a search query. And now these companies want to decide, do we show an ad or not? So this is determined by a real valued parameter. It's called a mainline reserve. And this basically tells you how many ads do we want to show in the mainline. What is the mainline? The mainline are these ads that are actually shown above the search results. So if you're using an ad blocker, I suggest to just switch this off for a moment. It's quite a bit of a different experience to surf the web without an ad block. So here, these are the ads that are shown above the search results. And again, this is the handle that we have. This is what we can control. So So we observe some user data, and then this mainline reserve we can set depending on the user data. Now, there's a complicated machinery that determines a discrete number, and this is the number of ads that are shown in the mainline, and this is always between 0 and 4. It's never ever more than 4. So it's between 0 and 4, and then at the end you either receive a click on this advertisement or not. And this data also comes in, and this is a huge amount of data that comes in every day. So you have billions of search queries, and then you always know, okay, what kind of mainline reserve was chosen and was there a click or not. And then, of course, what do you want as an advertisement company? You would like to increase the number of clicks here. And this is what I meant earlier. So this was, I mean, I didn't do it, of course, but the scientists, they told me that convincing the engineers to randomize this and also to log this afterwards was actually a big amount of work. What can you do then? You can play the same game. So what you see here is the mainline reserve. So this is just in relative numbers. So you observe some data that lies here. And then what you want to do is you just want to see, well, what would happen if I change the mainline reserve. It's a bit of a simplified picture now. And what you can do, for example, you can decrease this a bit, and then maybe you receive more average clicks per page. And now what you can do is you see these confidence intervals. Maybe as a side remark, so these confidence intervals, they actually contain two parts. And the inner part, this is the part that is actually increasing if you go far away from the data that you actually gathered. And why is this? Because this is indicating the uncertainty, because you're actually querying a sort of situation that is quite far away from what you have seen so far. And this, of course, becomes difficult. Statistically, why? Because then your weights will actually have a very large variance. There's a second component to the intervals. So there's the outer part, and this is just because you have a finite amount of data, of course, right? So you can decompose these intervals. So nevertheless, you have them. You can sort of predict, okay, this is probably what is going to happen, and then you just play the system. So you change the stream, and you get some data, and this is the new data point that you get. A tiny bit of motivation, maybe why did we choose this specific framework? This is really motivated by a causal question, because what turns out is that in the simplified picture of advertisement placement, it turns out that you know something about the causal structure. And I was, on purpose, I was not explicit about this, but if you look at the structure, there's actually an assumption behind, and this goes as follows. Whether a person clicks or not on an ad does not directly depend on the mainline reserve. And it cannot, because the mainline reserve is a continuous number between minus infinity and plus infinity. So the user never sees this number. So of course the event, whether he clicks or not, cannot depend on the mainline reserve directly. It doesn't know it. It only depends on the discrete number of ads shown in the mainline. And this is, if you like, it comes from a causal model. We're writing down a causal system, and it has some implications, namely conditional dependence statements, if you like. And you can exploit this for this task that I just explained quite nicely. Why? Because this is a real valued parameter, so these weights that we get in the estimator will behave much worse compared to weights that we would get if we only have a discrete random variable. Because the probabilities can't get so tiny, so the weights are much better behaved. You can sort of turn the crank, and what you see is that this has an effect on the size of the confidence intervals, and it's quite dramatic, I think. So this is with the old system, but now if you include the causal knowledge, what you see is you can actually get much better behaved confidence intervals. And this is just exploiting some causal knowledge that you have about the system. Good. Are there any questions about this?
The average is over the number of ads, or it's just per page?
Yeah, this is a complicated figure because, of course, this should depend on the covariates as well, right? So this is for a specific setting there. Yeah.
clarification question. Are you saying it only depends on the number of ads and not on how good a match they are?
Very good point. Of course, they also do depend on that. So there's a lot of things that go into here as well.
Exactly. There are a lot of confounders in this puzzle thing.
Yes, this is just not shown here, but this is of course what you know, right? So you know the context, and this is also something that you observe. So if you want to be more precise, this picture gets much more complicated. So, but you're right, you have additional sort of connections from the user data to the click. This is also the case, and you actually have a lot of feedback that you want to include as well, because actually showing more ads cannot be a solution, right? Because if you just show more ads, you get more clicks at the beginning, because the users will just mistake them for search results, but at some point they will get annoyed. Yeah. So this is actually maybe the last thing that I can say about this story. So what is also possible, you can imagine this, I guess. What is also possible is to optimize under constraints, because this is exactly what you don't want to do. Sometimes you don't just want to receive more clicks, but maybe you want to receive more clicks under the constraint that on average you're not showing more ads. Mathematically, this is super simple, because what you see here now, what we can do is the following. We have our objective function. These are the level plots of the black lines. Right, so the gradient goes like this. So we want to be here. This is receiving more and more clicks. But then we have another function, and this could be, for example, the number of ads that are shown, and the level plots you see here in the red lines. So if we start with a strategy that is here, and now we want to update the system, of course we would like to go towards higher regions, right? But then because we do not want to show more ads, what you just do is you project your gradient onto the orthogonal space of the gradient of the red function, right? I mean, this is what you can compute. You can also compute confidence intervals. I'm not showing the math here, but then you end up with an optimization that looks like this. So you start here and you're moving in this direction. Why? Because we want to go and we want to increase the value of the black function without changing the value of the red function. So what do? You just go along a line that is like orthogonal to the gradient of the red function, but still you see that the value of the black function is increased a tiny bit. These are things that you can do. So what I want to what I wanted to say with this story is really to say, well, if you have some parts of the data stream that you can change, that you have actively control over, there's actually a lot that you can exploit. Good. Any further questions? Then I would like to, sort of for 10 minutes or so, talk a bit about the second idea as well. So what happens if you don't...
Can you just ask a question about the blackjack or at the end?
No, you can do now. It's fine. Yeah.
So about the blackjack problem, I think, I think the performance of learning, your objective function, I think must be something like the expected value of the win or something like this. Now, it was quite smooth, meaning the variance was quite small, which is quite disappointing for a gambler, of course. When you are playing against the house, you know that your expected value would be negative, but you are playing for the variance, because so you want to have some values. I think you had some 1 or 2 points above, but is it possible to set it up like a multi-objective optimization problem, where you eventually come up, essentially you want to have an, maximize the expected value, also want to have some kind of as much variance as possible, so then you come up with a Pareto curve, and you let the gambler choose where they want to be on the curve. Is that possible to?
I think you can include it. Yeah, I'm not 100% sure whether I agree on this. So I see, of course, that a gambler would like to win sometimes. But having a big loss, of course, can also be a bit risky.
Exactly.
No, but it's a good point. I think you can do this with this constraint optimization idea. I think it should work exactly the same.
Optimization.
Yeah, of course, you have to sort of say which kind of variance you would like to have, right? But you're saying, well, then...
Yeah, the user will choose where on the Pareto curve they want to be.
I think that would be possible, yeah. One last word about this plot. It's averaged. The variance is a bit larger than it seems to be here, because this is always averaged about, I think, 100 games or so. Okay, so the last part of my talk, I would like to talk a bit about these natural changes in the stream. So now we are receiving data, and there's some heterogeneity in it, and I would just like to discuss a couple of ideas there. So let's suppose that we are in a situation where we actually have a prediction problem. So here we have our time index, we observe a couple of covariates, and we have one variable that we could call a target variable. Now, what you could see is that the system looks as follows. So we have, here's the time index, we have one target variable y that we are interested in predicting given x1, x2, and x3. Now, here's what happens. If you now plot, so on the right-hand side, what you see is a result of a linear model. So here we are regressing y on x1, x2, and x3 jointly, and I'm showing you the regression coefficients. And what you see is that they change over time. So here the scales are a bit different, but they all have a sort of a change in time. And this is because this is not IID data, but this is that we have some changes, some natural changes in the data. So here you can see, for example, there's probably a shift. Here's a change in the second moment and so on, but we don't know exactly what it is. So now, what can you do with this? So here, this is, by the way, this is a rolling window regression coefficient. So now we can always say, well, maybe you observe the system, and we mostly believe in the latest data that we have seen. So we sort of forget about the historic data. And here's just a sort of a food for thought. So there's another way of looking at this, and it turns out that if you don't look for the best prediction, where you just regress y on x1, x2, x3, but you look at other models as well, you actually may be able to find models that are invariant over time, but you have to actively search for this. So now on the next plot, what you show is exactly the same data, but now we just look at other models. So here we are regressing y only on x1. And then if you look at the regression coefficient, you see a change. But if you regress y only in x2, then actually you find that this regression coefficient is very stable. And what I would like to do in the last 10 minutes or so, I would like to discuss in which sense this could be actually a useful thing to look at. So here, it turns out that x2 is an invariant model, and this is from a certain perspective not surprising, because the underlying causal structure was that x2 is also really a cause for y, and this is something that remains invariant in our data. So the assumption here is that maybe there is some invariance in the data that is not apparent at first sight. So if you do a joint regression, you don't find it, but if you look more closely, then you may be able to find this. Why could this be an interesting thing to go for? So why would we be interested in a model like this? So if it's really a causal model, then what you can prove is that, it's easy to see that if you happen to find the causal model, then this is actually a model that is very robust in the sense that if you intervene on it, even if you have arbitrary interventions, it will still give you sort of the same predictive power as before. There is a formal relation that I'm not going to talk about now between this invariance and causality, and there are a couple of references where if you happen to be interested, you can read about this. But here it's really about finding these invariant models. So what you can do is you can look at, just to give you an idea of what would happen to real data. So this is I apologize if you've seen this before, but this is the exchange rate from the Swiss franc to euro over time. And I like this story a lot because I was living in Switzerland and I saved some money, and for a long time the exchange rate was more or less fixed to 1.2 by interventions from the Swiss National Bank. And then when I moved to Germany, I thought, okay, it doesn't matter when I transfer the money. So this is when I transferred the money. This was actually on a Thursday, and the next Saturday the course dropped, so I lost about 20%. So it's a bit like insider trading, but sort of the wrong way around. So then you see data like this, and you can be wondering, well, now let's try to model this. This is our target variable. We would like to model it, and these are variables that you can look at. So I'm by no means an expert in economy, but these are variables that we thought are related. And here this is our target exchange rate, and then you have a lot of indicator for the state of the economy. And then of course also some things that the Swiss National Bank has influence about. And now what you can do is you can look at different models. And now if you just do a joint regression model, for example, you would find that if you look at the residuals, they look like this. And I'm not saying that this is a bad model, I'm just saying this is a very non-invariant model, because what you see is that you have suddenly a period in time where your model sort of does something weird. So there the residuals are much larger than in other areas. And what we sort of try to suggest here is to say, well, maybe you should look for models that look a bit more like this. And this is actually one that is the most invariant that you can find. And here you see that the scale of the residuals is not necessarily smaller than this one, but it's more invariant. It's more sort of doing the same over time. And if you look at what kind of model this is a model that includes x2 and x7. If you look at this, there's the log returns of foreign currency investments of the Swiss National Bank and the log returns of Swiss GDP. And of course, this is very much a causal driver for the exchange rate. So this is, again, a benefit you can have by exploiting this invariance. Just maybe to mention, you can play this game further. You can look at much more complicated models as well. So this is now not a linear model anymore, but this is now one where you actually allow for a hidden variable, a binary hidden variable, because then what you can have is you can have a mixture model where your regression coefficients actually they switch between two different states. And this is what you can get as well. So here, what we would find is that actually this is a very stable model if you allow for two different states of your regression parameters. And this corresponds in a causal way to a hidden variable. This is in particular important. This was motivated by a study in Earth system science, because there what you often have is that you have two different responses of the system depending on a hidden variable. Let's say the soil moisture content is very important if you measure plant activity in relation to the radiation, for example. And I would like to conclude with one last idea. So what if there is more than one invariant model? So which one of them do we choose? So an answer would be just go for the best predictive model. And what this leads to is actually something that I would like to call anchor regression. So here, anchor, what does it stand for? It's really the time, something that you would like to be invariant against, and you can exchange the anchor against something else as well. But what does it do? We can now actually, if we believe in this idea of invariance, then we can now play the game and do a trade-off. We can now say, well, maybe we should be looking for models that are to a certain extent invariant with respect to the anchor and still have a predictive power. This gives you a whole new range of solutions, and this is surprisingly mathematically extremely simple to solve. So what we are going to do is we are looking for a solution that yields a small residual sum of squares, but at the same time we penalize, but now we don't penalize, for example, with a norm of B or something, but we are penalizing by non-invariance. So here A stands for anchor. You can think of the time. And what you want to have is that the residuals are really uncorrelated. So there's the covariance here, of course, but they are uncorrelated with respect to time. So you want to say that they are sort of always the same. This is the invariance. In this form, this is extremely simple to solve. I mean, one way of looking at this is it's just a quadratic program. And what it does, you can now analyze this if you like. Maybe some of you are familiar to instrumental variables. This is just if you let gamma go to infinity, you get instrumental variable solutions. These are very causal solutions. And if you have gamma going to 0, you get ordinary least squares, which is a very sort of predictive solution. And then you can be wondering, well, why should we want to do this, right? So, I mean, this is now something that trades off invariance and prediction. And one way to look at this is to say, well, it's actually the best thing you can do under a certain kind of intervention on the system. So you can get guarantees against certain perturbations of the system, something that you have seen before. So this is what this plot is supposed to indicate. So if you have certain sort of, these are solutions for B, this is what you get with anchor regression, and under certain sort of perturbations of the system, that's what I mean by MSE, you are actually better both than OLS or instrumental variables. A bit more formally, maybe I skip the more formal part here. But the idea is that we want to protect ourselves against these perturbations. Also, I think, according to the abstract, Peter Bühlmann is going to talk about something along these lines also tomorrow. Good. I would rather conclude. So this would be the message I'm trying to convey here. Your stream is not IID. Well, it doesn't matter. Try to exploit this. And I talked about two different ideas. So the first one was really where you have active control about one part of the system, and then you use randomization to find the optimal policy. And the second idea was, if you have changes in the system, you can actually try to find these invariant predictive models. And this is, again, I would like to stress this is a very different idea from minimizing residual sum of squares. And I have the impression combining these two ideas can actually be quite helpful. So if you think about systems like autonomous driving, right? So of course we want to be able to sort of be good in all the situations that we have seen so far, but maybe we also want to be sort of good in situations that we have not seen, right? And somehow solving these extrapolation problems, I think, is an important task for future in statistics, and maybe these ideas for invariance could play a role here. Okay, relation to causality, well, I just say yes, so I didn't talk about this much, but if you happen to be interested, I'm more than happy to talk about this. We just published a book on causality that is open access. You can just download the PDF from MIT Press. And with this, I would like to thank you very much for your attention.
Questions for Jonas?
So you've got some confidence interval, so this means you've got some probability coming from somewhere. So is the probability statements that you're making with respect to the randomization distribution, or do you have additional sources of error?
It's a good question, because it hints at something that is very fundamental actually for both of the stories that I talked about. This is sometimes called the autonomy assumption in causality. And it assumes the following. So if you have a system, think about like a joint distribution that factorizes with respect to a directed graph, then if you intervene on one part of the system, basically what you're doing, this is for example, the do calculus by Pearl, you're replacing one of these conditionals. And now the very fundamental assumption is that you only change this part. All the other conditionals will remain the same, right? And this is the underlying assumption here. For blackjack, I think it's a reasonable assumption. So this is the underlying measure. It's the underlying P.
And causation, that's called something like using the randomization to protect the Markov blanket of the system.
Yeah, but it's again, it makes this assumption, right? Because you randomize and you assume nothing else will change. In a lot of scenarios, this makes sense. In some, we have to be a bit careful. In advertisement, as I said, if you change your strategy like dramatically, maybe you suddenly like attract other users, or like this placebo effect. So this is the underlying assumption, which is important for the probability statement. I hope this answers roughly your question.
Okay.
So for the anchor regression that you had at the end, so I guess you really want there to be conditional independence, but you're in the optimization that you set up, you're sort of penalizing the conditional correlation. Or
yeah, it's a brilliant question, and this is what I'm not so happy about yet, because indeed this is a very specific choice, right? But this is one that we know how to optimize. So if you put something like your favorite independence test, we actually don't know how to solve this anymore, because it's of course very non-convex. So you can relax this a tiny bit, right? Because of course if you have higher moments of A, you get higher order dependencies. This is because A is just observed. It's trivial to include. But even higher order moments of the residuals, we don't know how to solve. I mean, even a second moment, then you get a quadratic program with quadratic constraints, but the matrix is not positive definite anymore, so you don't know how to do it. If you have an idea, it would be amazing. Yeah.
I don't want to press you on connection to causality, but just at a high level, if you have completely observational data, no interventions possible, how much of this carries over?
Of the second part, or?
Either.
So the second part really makes use of the heterogeneity in the data. right? And this is an interesting effect in the sense
Does
that
it matter, like if heterogeneity is completely
Gone?
observational and, well, you have no control over it. It's just
yeah, this is exactly the scenario what we are trying to do. So we are really saying, okay, let's say we don't have any control about it, it's really observational, but there has to be some heterogeneity, otherwise these methods will be uninformative. And the assumption that is the crucial assumption here is the anchor. So this we assume to be exogenous, and in the time setting of the streaming data, we believe that this is a reasonable assumption, right? Because, I mean,
you're really thinking time.
in other examples, what you can also think about is continents, different countries, or think about space or something, yeah. But something where you know that this is actually exogenous, so sometimes called a context variable for these constraint-based methods.
Your blackjack example, does it carry over to game theory? Like you are not playing against the house, but against somebody else, whose strategy also changes over time?
No, not directly.
Yeah.
And this is a violation of what Henry also asked about, right? Because then you're saying when you change the strategy, the underlying assumption here is that the rest remains the same. So there, I don't know an easy fix, but you would need to think about something if you play against an opponent. Maybe someone else has an idea.
Okay, thank you very much.
Thank you.